Alright, so welcome back to this final part. Now we are going to have a look at the actual code to generate this sampled polynomial, right? So here we go, this is the demo, and as usual for the drawing I'm using my plot widget. There are plenty of videos in when I explain how to do that. For example, there is the video for the for direction field, and so on. When I go into detail how this works, there is also other videos. I will put the link in the description, but there are plenty of videos where I go through that. But as you can see, I just pass in the points. So the points I'm interpolating to and the interpolated points. Basically, I generate the polynomial and then I sample the polynomial at a fixed steps, and then I just draw them. So I'm not going to spend time over this, right? But what we're going to look at is the polynomial interpolator class. And again, it's super simple class. It's just a wrap around our matrix class. So we pass in the points we want to interpolate through, right? And then we need to here in this empty list we're going to store the coefficients. So the first thing is to solve the linear system, actually to build the linear system, then solve it to compute the coefficient, and that's going to be really easy to do, right? So in order to do that, we need to build the matrix, and the matrix for that, if you remember, this is a system for 3 points, right? So let's say the P0 is 2 and 4, right? So we see that the final matrix for this guy is 1, 1, 1. Then we have, on the first line, we have the first degree of the x, sorry, the first, yes, the degree 1 of the x, so x0 is just 2, right? And then we have 2 to the second and dot 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 dot, and same for the other points, right? So we need to grab the x value and then build the row by keep adding and squaring the value, sorry, keep multiplying. So here we have 2 to the third, 2 to the fourth, based on how many points we have, right? So in this case we only have 3 points, so it's going to be 2 to the second. Let's say that P1 is, no, let's say 4 minus 2, right? So that's A0, A1, A2, and this is going to be 4, right? So then the next row is going to be 4 to the second. Then we have, let's say P2 is 7 and 1. This is going to be 7. Oops. 7 to the second. I forgot to write this one. So minus 2 and 1. So that's basically the matrix we need to build. This is going to be our solution vector that we plug in our system. This is going to be our matrix. And that's exactly what the solve function does. It's really simple, right? So we create an empty list, which is going to be our matrix buffer. So we loop the points. For each point, as a first, we append 1, because, you know, the first column is always 1, because it's the constant factor. Then we have an accumulator, which is basically we set it to x, right? And then we start looping by the size of the points minus 1. Because minus 1? Because we already added 1 element. So in this case, we're going to just loop 2 more times. And we're going to append the accumulator, which in the first case is going to be 2. But then you see that we multiply the accumulator by itself, so it will be to the second. And next time we're going to append it again. And then to the solution vector, we append the second value of the point, which is the y component, right? The points are not in mind of a list of float 2, right? So it's a list of x, y, x, y, dot 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 dot, like that, right? So once we have that, we build our matrix, we pass the points, sorry, the buffer of the matrix we build, we do the Gaussian elimination that we wrote ourselves, and then we set the solution vector as our coefficient. Then evaluating the polynomial is a piece of cake. You pass an x value, and then you're going to just evaluate the polynomial. So first you multiply and add together, right? So in this case, you add the first coefficient, then you multiply the coefficient for x to the first at the first power, then second coefficient x to the second power, and so on. And that's exactly what we're doing here. So we accumulate in our value, we multiply by the coefficient, we are looping the coefficient, and we multiply with the accumulator, and then we remultiply the accumulator by itself. So keep rising the power of x. Once we have that, we return the value. That's it. That's how we evaluate the points. Now, if we go back into the demo, you will see that that's exactly what we do. Here we have a series of points. We pass it to the polynomial interpolator. We call the solve. So now we can, once we solve the coefficient, then I'm going to loop. Actually, the screen is too small, so let me make it bigger. There we go. So here, I decided, okay, I want to compute 400 points. I'm going to sample 400 points over a range of 13. So this is simple math to basically just evaluate at a fixed step. Then I do a least comprehension where I'm going to evaluate 400 times an increasing value of x, right? Once I have that, I just draw the points. And we can see that this actually works because I can remove, let's say I want to remove 3 points. There we go. So I'm going to kill the current running one. I'm going to rerun it. And here we go. We just have 3 points. Here right now I'm actually sampling outside the range. So that's why it's overshooting like that. But that's basically the continuation of the polynomial, right? And if we add other points, it will behave accordingly, right? So that's one of the applications we can do Gaussian solvers. Maybe if you're a rigger, you're more interested in solving an RBF system to interpolate poses or stuff like that. But this was just a quick application, right, that you can use this for. So that's it. That's the end of this mini series, guys. I thought it was useful. Any feedback, let me know. The code is free on GitHub. Feel free to have a look. And that's it. Alright, guys. Bye-bye.